Today we're going to be solving binary search 704. This is quite an easy problem, but I will walk you through it. Now, given an array of integers, nums, which is sorted in ascending order, and an integer target, write a function to search target in nums. If target exists, return its index. You must write an algorithm O log of n. Okay, an example is -1, 0, 3, 5, 9, 2, 12. Target is 9. So 9 is at the fourth index, right? So 0, 1, 2, 3, 4. Sorry, 0, 1, 2, 3, 4. 9 is at the fourth index. You have to return 4. If not, return -1. Now the intuition behind binary search is, now because the array is sorted, let us look at the middle element. So the middle element would be 5. Now 9 is obviously greater than 5. So we do not need to search on the left hand side of the middle element. We can directly skip the left half and search in the right half. Correct? You would reduce your search space, which should save on time. Now let's do a naive solution, which is a linear time, that would be O of n, where we search each element in the array and check if it is the required value. And then let's try and do the optimal solution. So for I in nums, we need to return the index, so we need to do a range operation, range of length of nums. If nums of I equal to the target, return the index, right? Now return -1 if we have not found the number. Now this should work. Okay, you can submit that, but it's not ideal. I think we would get a time limit exceeded on some of the larger cases. If it did work, but it's quite slow, as you can see, 196. We can do much faster. So how do you approach a binary search problem? You define the bounds of your search space, which is the starting point and the ending point. So the high would be the length of the number array -1, because the last index is -1 minus the length of it, and the low would be 0. So now while low is lesser than or equal to high, you can calculate the mid. So for a given search space, now the low is -1 and the high is 12. Actually low is 0 and high is 0, 1, 2, 3, 4, 5. So from 0 to 5, the mid would be 5, right? So now we have to calculate the mid of this search space. So that would be high, low. Okay, now we compare the value at the mid position, so that is 5. So now if nums of mid is equal to the target, then you can return mid. So that means we found the target at mid. We got lucky. Now if nums of mid is greater than the target. Now let's say the target was 5 and the target was 3 and we found 5 at the middle position. So that means 5 is too high, so we need to search in the lower values, right? We need to search in the previous half, so we need to search in this half. So we can now reduce the high value to this, so that we search in this instead of searching in all of this. So we need to ignore these values, right? So we need to reduce the high. So then the high would be equal to mid -1. You need to make sure not to equate it to mid, otherwise it would run in an infinite loop. Now the other condition would be, we found, let's say the target is 9, so and the middle is 5. So we can ignore these values because we know 9 is never going to be lesser than 5, right? So we can ignore the lower values, so we can ignore this. So that would mean bringing the low pointer up to the next half, the second half, the higher half. So the low would be equal to mid +1, and this would keep on running and the search space would keep on reducing until mid is equal to target. Now, even after all this, if we have not returned the mid value, that means we have not found the element, and you can return -1. You can go ahead and submit that, and it's much faster, 55%. Don't get too worried if your speed is not good sometimes, because it depends on the Leetcode server as well, but this is the most optimal solution. It runs in O log of n. Now, why does it run in O log of n? Because you're dividing the search space by 2 every time. So what would have been 10 operations or 10 for loops in a linear solution, you would only search for, now the first case would be search 10 elements, second case would be search 5 elements, in the third case search 3 elements, and then 2 elements, and then 1. So a maximum of 4 searches for 10. Now when a very big search space is there for, like, say, 1,000,000 data, it will be much exponentially faster than linear solution. So that's why it's a log of n solution. Hope you liked the video. Please like and subscribe.